Hey everyone, for the very last topic of the seminar, I want to go over some advanced topics, just a few interesting samplings of some things I thought would be interesting to think about as you're going into more advanced PCB design now that you've learned how to make the basics of schematics and layout and some things to think about as you move forward. So this is the last video for the seminar. One thing you want to start thinking about is thermal management. When things get hot, they expand and contract and can break, and also things don't work at high temperatures. So like a lot of ICs are limited by the temperature that they can run at. You know, if it's depending on if it's auto grade or military grade or whatever, it can maybe stop working at 80 degrees or 120 degrees. Some ICs have thermal shut off, so they'll actually just turn off, and some will just kind of stop working because different like resistances and things can basically change at high temperatures and then things stop working. So ideally you're going to want to keep things around room temperature, but if you have, especially with high power systems, things can get kind of hot, especially certain chips that do, power converting or that kind of thing are very high in computation. So there's a few different ways to manage this and try to keep things roughly room temperature. So using like bigger fat traces for high power things or planes like power planes and ground planes when you can is definitely one of the better ways to deal with this. So you really don't want tiny thin traces that are carrying a lot of current because those can really heat up and break things. For certain ICs, this for kind of switching regulators or for ICs that are having computation like a computer or something like that, you can also just throw a heatsink on there. These are really good tools for dissipating heat, and then fans if necessary, depending on how hot these things get. If you're working with some like mechanical engineers, or if you're doing the mechanical design yourself, you can consider airflow in whatever system you're putting this in. So if you're mounting this inside of a chassis, maybe ensure that there's in some way airflow throughout the system. We talked a little bit about this during the layout, but this idea of thermal relief. So if you'll recall from the layout slides, this is like a thermal relief connection. And the idea is that if you're soldering to this and it's completely connected to this really huge plane, it might be difficult for you to solder to it because heat will just dissipate into the surrounding plane as opposed to onto the pad that you're trying to solder. And it might be very difficult to solder to that. And also if you have one side that has thermal relief and one side that doesn't, or one side is just connected to a trace, for instance, and one side is connected to a huge plane, the chip might solder unevenly, and that can lead to problems during reflow if you're soldering it that way. So just something to think about when you decide to or to not use thermal relief. This is just a setting that you can select when you're making your planes, your like power and your ground planes, and you can change it for individual connections as well. Another thing to start thinking about as you move to higher speed designs and more involved communication protocols is impedance control. So a lot of high-speed signals, they have like designated impedances so that when you connect them, it's continuous across, if you like plug in an HDMI header or a USB or Ethernet, it should be continuous across that boundary to improve signal integrity. So, for instance, like USB, the designated impedance for that is 90 ohms, and HDMI I think is 100 or also 90. And if you'll recall impedance from the very first lecture, impedance is basically like resistance, but in the frequency domain. So you have to consider capacitance, inductance, and resistance when you're calculating the total impedance, and that will change depending on if you'll recall the equation for resistance. It will depend on how thin the traces are, and then the capacitance will depend on how far spaced apart they are. So a lot of manufacturers will, given a Stackup, will give you an impedance calculator for what these trace widths should be, what the spacing between them should be, maximum lengths that they can be. If you have really, really, really long traces, you're adding a lot of resistance and capacitance to that line, so you're adding a lot of impedance. So there are calculators for these kinds of things. If you want to plug them in first, I know Sierra Circuits has a pretty good one. Another few things about high-speed signals in general, often they're in these things called differential pairs. So if you look at this graph, you'll see, or not graph, this is this layout, you'll see that they are kind of like paired up in pairs of two. And that's intentional. These are differential pairs. And the idea of this is that if you have one signal traveling along, around other chips and throughout the board, and you have any kind of like noise spike, whether that's like interference from a different signal or something like that, it could change like fundamentally. So this is, let's say we flip this would be a 0 and then it goes to a 1 and goes back to a 0. But here, if you add this noise to it, it goes 0, 0, 1, 0, which is not what you want. And then if you read the signal on the other side, you would be reading the wrong information. However, If you then instead split the signal up and send it as a pair of signals, then any noise that's injected onto this line gets injected onto both. And then you take the difference at the end of between the two signals. And because that is something called common mode noise, so it's common between the two signals, and when you take the difference between them, there's no difference between them when you look at the noise. So it'll actually come out as you intended it, because this is on both lines. And the only thing you have to worry about is then differential noise. If a signal gets paired to only one half of the differential pair and not the other half, that's when you have to worry about that kind of thing. But it's a really good way to decrease noise and protect against EMI in your system. And that's why these are paired up like this. If you're wondering what these weird bumps are on these lines, that's a good question. This is something called length tuning. So let's say you're going around, you're looking at these two traces, and you see that this one is going, you're taking a turn, this one is going to be shorter than this one. So now all of a sudden this one's longer, and let's say, this is a pretty fast signal. This signal gets here, this is a shorter path. This signal will get here faster, and the signal will get here later, and they might actually be off in terms of the clock cycle, and then you're comparing the wrong signals. So you don't want signals to travel at different, to get to the end at different speeds. So you want them to be as close as possible in terms of their length, in terms of the differential pairs. So you can just add little these little wiggles that just match the lengths of the pairs, so that your signals are arriving at the same time. And Altium has a tool for this. Okay, Stackup management. We talked a little bit about Stackup again in the layout lectures, but just to remind you, this is just the order of your like layers inside of your board. So, all of your metal layers. We've been working only with 2-layer boards, but when you move on to 4-layer boards, then is when you just start to have some semblance of control over what order you can put things in. So when you have a 4-layer board, there's a bunch of different orders in which you can put ground, power, and signal planes. So in this case, you wouldn't have a ground plane just covering the top. You wouldn't have a pour over the top. You'd have an entire plane just dedicated to being ground, and one plane dedicated to being power. Or not. You could make these all 4 signal layers. It's a pretty bad idea. That's not really very useful at that point. So usually you would have at least 1 or 2 ground and power planes. Ideally, you want as many ground planes as possible because they're very consistent and they shield between layers and they minimize your ground paths. So maximizing the number of ground planes you have is really great. But also you want, if you have a lot of things that are connected to power, which you obviously will if you have a lot of things connected to ground, it's also very useful to have that distributed along the board, so you don't have to have these smaller traces, winding their way around the board for power, because that's going to increase like the resistance on the line and waste power. So there are a bunch of different ways that you can distribute these. If you have ground on the inside, it will shield the signal layers from each other. But if you have ground on the outside, it will shield the signal layers from external EMI and things like that. And we can talk a little bit about the different things that will cause that in a second. But ideally, you'll find out whether or not your problem is, okay, other things in the system or external to the system are causing a lot of noise, and that's our problem. Then you want to put the ground planes on the outside. But if you're having something more like, okay, the really noisy, power converter here is causing this really sensitive gigabit Ethernet line to screw up sometimes, then maybe you're going to want to put ground planes in the middle to shield them from each other and put those on opposite layers. So just some different things to consider. And then you can do the same thing with power and ground planes. Ideally, when you do your impedance control, you're going to want to put your traces on top of a ground plane, because it's changing, it's consistent, and then you can have very short ground control loops, which will decrease the inductance in your system. Ground control loops, just ground loops, which will reduce the overall inductance and therefore decrease the impedance changes in your system. So that's something you want to think about if you're have a signal here, if you have Ethernet here, you're going to want to put it on top of the ground. You wouldn't want to put it on top of power. Okay, another concept, blind and buried vias. So far, we've only been working with vias that go all the way through. They're plated through holes. They go all the way from one layer to another. And when you have a 2-layer board, that's really all that makes sense. But let's say you have a 4-layer board, and all of a sudden you want to route things here, or you want to have a ground plane here. This will interrupt that plane. This will interrupt. You have to route around that on a lower level. So maybe you don't want that. Maybe you have a really dense board, and you want to be able to route through things without having to go around all of these different vias that you've placed that don't even have anything to do with this layer, because it's just going from the top to the bottom. So you can use things called either blind or buried vias. So this is blind because it doesn't go all the way through, and this is buried because it's entirely within the board. This is possible. You just do this before you do your stack up, or you do it with like lasers, and there's different ways of going about doing this, but it's more expensive because you're not just drilling holes anymore. You're now doing a whole different process. But if you have a really dense board, let's say you move up to a 16-layer board, how could you not do this, right? It'd be very difficult, and at that point, adding more layers wouldn't be very helpful because they're all covered in vias from all these different layers. So, just an option to think about as you go into more professional and more complex PCB design. Testing, everyone's favorite part, right? Is testing your board, and there's this broad concept called EMC, which is electromagnetic compatibility. You've heard me talking a lot about EMI in different lectures. Well, that's one category of this. It's electromagnetic interference, and then you test for compatibility in terms of both emission and immunity. So emission is like, what does your board emit? So what's coming out of your board? What noise is your board creating? And then immunity is your board's susceptibility to interference from other sources. And conducted and radiated. So radiated is like if your board is emitting just kind of like radio waves, or not necessarily radio waves, just like just noise out into the universe. This could be problematic for communication systems, for wireless communication systems, and that kind of thing. And then conducted is back into the power line. So let's say you have, you have this plugged into the wall. Is it conducting any kind of noise back into the power system? And that can be bad for other devices that are plugged into the same system. So when you're actually creating boards to go into products that are sold, you need to follow certain rules of what you're allowed to emit and conduct, and what your immunity has to be and what your emissions have to be. And you can do a lot of testing to determine what this is. And some of the rules that I've taught you guys, reducing ground loops and keeping certain signals close together and that kind of thing. Those kind of things really do help with reducing your EMI and helping you pass these tests and keep your devices safe. And there's different rules for like different frequencies. So you can't emit as much in frequencies that are dedicated as communication spaces and that kind of thing. And it depends what kind of device you have. Are you making a drone, or are you making a blender? Those are going to have different rules of what you are and are not allowed to emit and conduct. There's also some testing with high power. So if your device is like accidentally powered incorrectly due to bad wiring in your house, it shouldn't just like zap you and kill you, ideally. And then obviously smaller things like it shouldn't be dangerous if someone likes taking apart your device, or if there's some kind of like if something metal falls in your device. You can't have just these random things going wrong and causing serious problems. So there's certain rules about if you have like AC and DC power, you have to space them out, and you can't have like connected planes internally for them. And so there's some different rules that you have to think about. And I'm not going to go into all of it right now, but just something to think about if you're going to be doing anything where you plug a board directly into the wall. You cannot just plug it into the wall, go through a converter, and call it a day. There are rules and regulations that you should follow to make that safe. Protecting your board. So you made a board and now you want to put it in the device, but the device is being susceptible to moisture or dust, or it's in a shop, so it's getting materials on it. What are you gonna do to keep that safe? So one thing you can do is called conformal coating. And you can see it's basically just this epoxy that goes over a board and covers everything, so that it's not going to be as susceptible to moisture or dust or dirt or whatever it's around. It also prevents shorts. So if you're dropping metal on this, it's not going to short the pins because they're covered in basically a plastic. Don't just put this on boards right away, because if you want to, let's say you decide to change some chip or you want to test something, it's really hard to get under this. You have to kind of peel it off, and it's kind of a pain. So you really only would put this on you prototype something, you tested it, you made sure you're really happy with it, and then once you're mass manufacturing it and putting it in all of your drones or whatever it is that you're making, then you can conformal coat it and protect it from moisture and sand, etc. Whatever it is that you're protecting against. Another more obvious solution is a mechanical enclosure. You can just put this thing in a box that's waterproof or airtight, so it's not going to have any problems with sand or dust or whatever it is. And it can also protect from high voltage as well. So if you have a board that's connected to hundreds of volts, don't just leave it open and out in the air, because if someone walks by and touches it, they're gonna get zapped. I've done this many times on PCBs where I'm working with them, and that's the one thing if you're actually like currently working with it and trying to test it in some way, you can't really protect against that as much, but someone else who's like interacting with your system should not get zapped just by touching your board. So protecting against high voltage systems should definitely always cover anything that has exposed metal that's a high voltage. Flex boards. So these are really cool. I haven't actually made any of these before, but I think they're really interesting. And if you go into design, you probably will end up at least using these at some point. Flex boards, just flexible boards. They just bend, as you can see. Like they're basically just like if you've ever used a connector to like a camera or something like that, these are often used. Like for a Raspberry Pi, for instance, the connector that goes to the camera, it's a flex board, and it doesn't need to have components on it, but sometimes it can just be cables, but sometimes you can also put components on it and make it like a full PCB. It's very useful for maintaining impedance matching. So you want to, if you, instead of just plugging jumper wires into something or random wires, you can have, designated widths and spacing planes for your cables themselves. They can also be PCBs, which is super useful for connecting boards that you want to maintain impedance matching. So for instance, like with a camera, it's pretty high speed. It's a lot of data. So you want to maintain that. So that's why the Raspberry Pi uses that as a connector for the camera module. And there's like rigid flex where like parts of it are, so like this could be all be like, one board where it's laminated together. So that this is kind of like stuck in the middle of this board and connected to it. And so that parts of it are flexible and parts of it are rigid. And then it's one big PCB that can bend around whatever mechanical constraints you have. So those are pretty interesting. Like I said, I haven't used them personally, but they're really cool. And hopefully someday I will get to make some. And maybe you guys will too. So that's all I have for some advanced topics, just some things to think about. None of this is necessary for your final projects or anything, just cool things to think about as you continue on your PCB journey. I hope you guys have learned a lot from this. Thank you.